This section introduces the power method, which is one of the simplest eigenvalue algorithms. Given a metric A, a square metric, the algorithm will produce a number lambda, which is the largest eigenvalue of A in modulus, and a non-zero vector V, which is a corresponding eigenvector of lambda, satisfying this equation AB equals lambda V. For the method, we'll assume the following. A has n eigenvalues, lambda 1 to lambda n, and n associate eigenvectors v1 to vn, which are linearly dependent. And precisely one eigenvalue is largest in magnitude. Say lambda 1 is the largest one. That means in magnitude, lambda 1 is larger than any other eigenvalues. The power method will try to find lambda 1 and its corresponding eigenvector v1. Okay, now let's derive the method. We assumed that eigenvectors are linearly independent. It's n-dimensional space, and there are n linearly independent, which means this set is a basis. So that for any vector x in Rn, we can express it in this linear combination. So x is the summation of, now that is a linear combination of the linear independent eigenvectors as well as possible with that assumption. We multiply both sides a, then now ax. Now for a, we apply a, multiply a term by term. So in jth term, avj. Now avj is lambda j vj. We apply a one more time so that a squared ax, which is same as a times ax, which is this one. Now again we multiply a term by term, exactly same a. Then now we reach at this result, lambda j squared. As k increases, in general, we have here a to the kx is now this linear combination with lambda j to the k. Now we can rewrite this one in this way. Now lambda 1 will be factored out. Then we have here lambda 1 to the k on the bottom as the denominator. Let's see the detail. Now first, now here there is a summation trace 1 to n, trace 1, trace 2, trace that is trace n. Now this quantity lambda 1 over lambda 1 is 1, but this one is smaller than 1 in modulus. We assumed, and lambda 1 is largest in modulus, and only this only lambda 1 is larger. Precisely one eigenvalue is strictly larger than any other eigenvalues. That's our assumption, so that this one is smaller than 1 in modulus, so that as k increases, it will approach 0, and again it will approach 0. So for every term will approach 0, which means that in limit a to the kx is now here, after taking limit here, limit x approach, k approaches x infinity, lambda 1 to the k, beta 1, that is 1, and v1. So we reach at this right side, right? Okay. This equation is not yet useful. The reason is, if magnitude of lambda 1 is less than 1, then it will converge to 0. And once the magnitude of lambda 1 is larger than 1, then it will blow up. So it is not so useful. To overcome this issue, we may scale a to the kx in an appropriate manner so that the limit in this equation is finite and non-zero, so that we can find the eigenvector. Now, the scaling factor eventually will become the eigenvalue of lambda 1. Let's see a pseudocode of the power iteration. Start with a non-zero vector x. Now we initialize the iteration x0 by scaling its magnitude in L infinity norm. So length of x0 in L infinity norm is 1. Now in iteration, we first multiply a and save into a temporal array y and measure the magnitude, so that we assign the result to mu and divide by mu to get the next iterate. So scale by the magnitude of the product, and we get new iterates. That's the power method, quite simple. Now let's try to get properties. Because of scaling, for every k, x to the k has length 1 in L infinity norm. Now, when k is sufficiently large, then as in this equation, here we may consider only the first term, and we may ignore the others. Relatively, these are way smaller than this one. It's ignorable. Okay. Now, xk is obtained in this way. K times of multiplication of a, now scaled by, from the beginning, mu1, mu2, mu3, and up to k. And we divide the product by the scalars. Okay. Now, for this term, we try to use only select the first term, then that one in the linear combination. So it is approximation. For xk plus 1, similarly, we reach at this one. Now, we know that for every k, so the k or k plus 1, this have the magnitude 1 in an infinity norm. So that right side over there must have magnitude 1. Now, we compare these two terms. This term has extra and is minus 1 power, so that mu k plus 1, j is moving from 1 to k plus 1. For this one, j is 1 to k, so that this one has extra term mu k plus 1. Now, over there, and for lambda 1, this is k plus 1 power, lambda 1 k, so it has extra lambda 1 on the top, lambda 1, on the bottom, mu k plus 1. So eventually, the ratio must be around 1. Because length 1, length 1. So that every else the same, only the difference between these two is on the bottom, mu k plus 1, on the top, lambda 1. So that the ratio must be around 1, right? Okay, here, so that means that mu k will converge to lambda 1 in modulus, because mu k is non-negative, and in fact in general is positive, so that it is approaching to absolute value of lambda 1. Now here xk will converge to a v1. This convergence has a speed in this way. Each time here the dominant error in this iteration is this one, and that will be reduced by, in each iteration, the power lambda 2 over lambda 1 will be multiplied again in each multiplication, so that this part is now converging to 0 along with the factor lambda 2 over lambda 1. So that we can say here in the theory, now mu k is converging to the absolute value of lambda 1 with error here now dominated by lambda 2 over lambda 1. So that after k iteration, there's k power will appear. Okay? So error is reduced by this factor each time. We have assumed that A has n linearly independent eigenvectors, which is the same as A is diagonalizable. That means that A can be written in this form. A is P, D, P inverse. P is the collection of eigenvectors, and D is the diagonal matrix having the eigenvalues. Okay. Let's see this example. We have a matrix, and here by using some software, that is Maple sentence, we can get 631, which are eigenvalues, and these are corresponding eigenvectors. For 6, this is the eigenvector. For 3, an eigenvector. For 1, 0, 1, 1 is a corresponding eigenvector. We know that, and for this metric, let's try to find the largest eigenvalue and corresponding eigenvector, and we'll see how it is converging. Okay, this is the Maple implementation, and start with x 1 0 0 and multiplication, and now L infinum is measured and saved into mu k, and scale to get new iterate. And now in each iteration, we try to print out k value and mu k, and also the x, so that it will convert to the vector. And then now we try to measure the error. Once mu k is converting to 6, then now we can measure the distance between 6 and mu k to see how the error is reduced in each iteration. Okay, that's the result after 10 iterations. As you can see here, now mu k is converting to 6, but not yet complete. Now the eigenvector 1, here the exact eigenvector is 1 minus and 1. Now it is 1 around the minus 1 and around the 1. Not yet complete, but anyway, it is approaching to 1 minus 1 and 1. Now this is the error. Can you see half? Okay, again half, and again half. About half. And here, in each iteration, the error is reduced by half to listeners. Lambda 2 over lambda 1 is half. We know that lambda 1, lambda 2, 3 over 6 is half. So symptotically, in each iteration, the error is reduced by 2. So error becomes half in each iteration. Okay. Okay, this is end of part 1. We'll continue in the second part. Thank you.